The sun's light arrives without ceremony, not as a spotlight, not as a beacon, but as a steady flood of radiation that has filled every day of human history. It crosses 93 million miles of space and meets the thin skin of Earth's atmosphere, then the surface of oceans, deserts, leaves, and stone. It warms, it illuminates, it pushes chemistry forward, and it sets the tempo of biology in the quiet regularity of daylight. It is easy to forget that sunlight is not a simple thing. It is a physical spectrum, a distribution of energy across wavelengths, filtered and reshaped by gas and dust, and then interpreted by the nervous system as color. For a calmer viewing experience, watch in full screen and keep the volume low and steady. If this kind of patient, science-forward narration is worth returning to, subscribing helps you find the next long listen. The sun is often described as yellow, in drawings, in flags, in the shorthand of childhood. And yet, when measured, sunlight in space is close to white, a broad mix of wavelengths that spans a visible band and extends far into the infrared and the ultraviolet. The difference between yellow and white is not a contradiction, so much as a lesson. Color is not only a property of the light source. It is also a property of the path the light takes, the medium it traverses, and the kind of eyes and brains doing the interpretation. When imagining the sun in other colors, the first task is to define what color could mean for a star. A star is not painted. It does not emit a single pure wavelength the way a laser can. It radiates thermally, and thermal radiation is inherently broad. Even when a star looks red or blue to an observer, the star is still emitting across a range. The adjective is an approximation, a compression of a spectrum into a name that a human visual system can carry. So, the premise becomes richer when it is made precise. A sun that is other colors means a sun with a different spectral power distribution, a different allocation of emitted energy as a function of wavelength. That difference can arise from a different surface temperature, a different atmospheric composition in the sun's own outer layers that reshapes the outgoing spectrum, or a filtering process between the sun and Earth. Each route has different consequences, and some combinations are physically inconsistent unless other stellar properties change alongside them. Color begins with electromagnetism. Light is an electromagnetic wave, oscillating electric and magnetic fields that propagate through space at a constant speed in vacuum. Those oscillations can have different wavelengths, the distance between successive peaks, and different frequencies, how many oscillations pass a point each second. Wavelength and frequency are linked. Higher frequency means shorter wavelength, and lower frequency means longer wavelength. Photon energy follows frequency. Each photon carries energy equal to Planck's constant times the frequency. Shorter wavelength light corresponds to more energetic photons, capable of driving chemical reactions that longer wavelengths cannot. The human visible range is a narrow slice of this electromagnetic continuum. Roughly, it spans from about 400 nanometers at the violet end to about 700 nanometers at the deep red end. That band is not special to physics. It is special to us. It is where the sun's emission is strong and where Earth's atmosphere is relatively transparent, and it is where the molecules of our visual pigments evolve to respond. Outside this band, there is ultraviolet, with photons energetic enough to break chemical bonds and damage DNA, and infrared, with photons less energetic but abundant in thermal processes, felt as warmth. If a sun spectrum shifts, then everything that depends on those photons shifts too. Not only what the world looks like, but what the world is. Photosynthesis is not merely about brightness. It is about photon energy and absorption bands. Climate is not merely about total watts. It is about which wavelengths are absorbed by which materials, and where that absorption occurs in the atmosphere or at the surface. Technology is not merely about daylight. It is about how semiconductors respond to different photon energies, how polymers degrade under ultraviolet, how satellite charging depends on spectral output, and how radiative heating profiles change when the spectrum moves. To understand how the sun can be white in one context and yellow in another, it helps to look at what the sun emits before the atmosphere touches it. The sun's photosphere, the layer from which most visible light escapes, has an effective temperature near 5,770 Kelvin. That number does not mean that the photosphere is a perfectly uniform surface of that exact temperature. It means that if the sun were a perfect blackbody radiator, an ideal object that absorbs all incoming radiation and emits a characteristic thermal spectrum determined only by temperature, then a blackbody at about 5,770 Kelvin would have roughly the same total emitted power per unit area and a similar spectral shape to what the sun emits. Blackbody radiation is a foundational concept because it ties color to temperature in a mathematically strict way. A blackbody spectrum is continuous. It has a peak, and it falls off on either side. As temperature increases, the peak shifts to shorter wavelengths, and the total emitted power rises steeply. Wien's displacement law gives a relationship for the peak wavelength. Peak wavelength equals a constant divided by temperature. For 5770 Kelvin, the peak in wavelength terms falls in a visible near the green part of the spectrum around 500 nanometers. That sounds like it should make the sun green. But a broad spectrum peaking near green does not appear green, because the sun emits plenty of red and blue as well. The combined stimulation of the three classes of cone cells in human eyes produces a near-white sensation under neutral conditions. The sun spectrum is not a smooth blackbody curve. Superimposed on it are absorption lines, dark notches where specific wavelengths are partially removed because atoms and ions in the sun's outer layers absorb those photons. Hydrogen, sodium, calcium, iron, and many other elements create a forest of spectral lines. These lines are the basis of stellar spectroscopy. From them, astronomers infer composition, temperature, pressure, and motion, but the broad overall shape still resembles a thermal distribution. In space, if an observer's eyes were adapted to brightness and if the background were dark, the sun would not look like a saturated yellow disk. It would look white with perhaps a slight warm tint, because human perception under intense light and adaptation tends toward white balance. On Earth, however, the atmosphere acts like a filter, Rayleigh scattering by molecules much smaller than the wavelength of light, scatters shorter wavelengths more strongly, proportional to about the inverse fourth power wavelength. Blue light is scattered more than red. Overhead, where the sunlight's path through the atmosphere is short, some blue is scattered out of the direct beam and into the sky, making the sky blue and the sun's disk slightly yellowish by subtraction. Near the horizon, when the sun is low, the path length through the atmosphere is much longer. More blue and green are scattered away and absorbed, leaving the direct sunlight richer in longer wavelengths. The sun then appears orange or red, and the sky can shift through gradient of color depending on aerosols and dust. Yes, scattering, caused by larger particles like aerosols, water droplets, and dust, scatters light less strongly depending on wavelength, often producing the whitening of haze and the glare around the sun. The balance between Rayleigh and Mie scattering shapes the quality of daylight, the softness of shadows, and the color of the sky. Even without changing the sun at all, Earth can make the sun appear different colors simply by changing the filtering medium. Volcanic eruptions, forest fires, desert dust storms, and pollution can all shift the perceived solar color by adding particulate scattering and absorption. In some rare conditions, heavy aerosols can make the sun look more muted, even bluish in extreme cases, not because the sun emits blue light preferentially, but because the complex scattering and absorption can remove reds more than blues along the line of sight. Yet, those are changes in appearance. The deeper scenario is a sun that physically emits a different spectrum. To imagine that, one must respect constraints. A star's emitted spectrum is linked to its temperature, and its temperature is linked to its luminosity and radius through the Stefan-Boltzmann law. Luminosity equals surface area times a constant times temperature to the fourth power. If the sun's temperature changes while its radius stays the same, its total luminosity changes dramatically. If its luminosity changes, Earth's climate changes, perhaps catastrophically. If the sun's radius changes too, some luminosity changes can be compensated. But then orbital and tidal dynamics are not directly affected by radius, yet stellar evolution and stability are. A star cannot simply decide to be blue today and red tomorrow, while everything else stays identical. So the cleanest way to proceed is to consider families of physically coherent scenarios, each defined by which parameters are allowed to change and which are held fixed. One family changes the sun's effective temperature, accepting that luminosity will change unless radius changes accordingly. Another family keeps total luminosity at Earth's orbit roughly the same by allowing radius to adjust when temperature changes. A third family keeps the sun itself the same, but applies a spectral filter between the sun and Earth, perhaps in the upper atmosphere or in orbit, which reshapes the spectrum without changing total incoming energy by much, depending on the filter. A fourth family considers changes in the sun's outer atmosphere, its spectral lines and continuum opacity, altering the detailed shape within the visible range without drastically changing effective temperature. Each of these yields a sun that is other colors in different senses, and each would build a different Earth. Start with the most intuitive color names. A red sun suggests light weighted toward longer wavelengths. A blue sun suggests light weighted toward shorter wavelengths. A green sun suggests something trickier, because green is not naturally the dominant perceived color of thermal emitters. A violet sun suggests even shorter wavelengths, pushing into ultraviolet. A white sun might simply mean a spectrum balance across visible wavelengths. But the sun is already close to that in space. The story, then, is not about a paint swatch. It is about the spectrum and how ecosystems, climate, and technology co-evolve with it. In ordinary life, color is often treated as a property of objects. A leaf is green, a tomato is red. But in physics, objects do not have color in isolation. They have reflecting spectra. They reflect or absorb different wavelengths to different degrees. The light shining on them has its own spectrum. The product of the illumination spectrum and the object's reflecting spectrum determines the spectrum of light reaching the eye. The eye then samples its spectrum with 3 cone types, each sensitive to overlapping bands. The brain interprets those signals into perceived colors. This means that changing the sun spectrum would change the apparent colors of everything, even if the object's reflectance properties stayed the same. Many objects will look unfamiliar not because they have changed, but because the light probing them has changed. Human trichromatic vision is an evolved compromise. Our 3 cone types are often labeled S, M, and L, roughly sensitive to short, medium, and long wavelengths, with peaks in the blue, green, and yellow-green regions. The overlaps are substantial. The brain's color perception is based on relative activation patterns. Under different illumination, color constancy mechanisms attempt to maintain stable object color perception by adjusting internal white balance. But color constancy has limits, and in extreme spectral shifts, familiar categories would break. Imagine a sun whose spectrum is shifted redward, so that the peak moves into the orange or red region. One way to achieve this is to lower the sun's effective temperature. A black body at about 4,000 Kelvin peaks in the red-orange region and emits relatively less blue. Such a star would look reddish. But if the sun's radius stayed the same, its luminosity would drop sharply, because luminosity scales with temperature to the 4th power. Dropping from 5770 to 4000 Kelvin reduces luminosity by a factor of roughly 4000/5770 caret 4, which is around 0.23. Earth would receive less than a quarter of its current solar power. The planet would freeze on a global scale. Oceans would ice over, atmospheric circulation would collapse into a colder regime, and the habitable zone would shift inward. To preserve Earth-like total insolation while changing color, the star would need a larger radius. A cooler star can have the same luminosity if it has a larger surface area, meaning a larger radius. Specifically, radius would have to increase by the inverse square temperature ratio, roughly proportional to T_current/T_nu. Caret 2, to keep luminosity constant. With 4,000 Kelvin, radius would need to be about 5770/4000. Caret 2 is almost equal to 2.08 times the current sun's radius. That is an enormous physical change. It implies a different type of star, more like a subgiant, with different internal structure and evolution. But as a coherent scenario, an Earth at $1 receiving the same total power from a larger, cooler star is at least physically definable. In that scenario, daylight would be dimmer in the blue. The sky's scattered light depends strongly on the presence of short wavelengths. Rayleigh scattering would still preferentially scatter whatever short wavelengths exist, but if the spectrum has less blue to begin with, the sky would be less saturated blue and more pale, perhaps tending toward a muted cyan or even a whitish tone, depending on aerosol content. The sun's disk would appear deeper orange. Twilight would be extended and dominated by long wavelengths, with less of the vivid purples that come from the combination of red direct light and scattered blue skylight. The consequences for biology would be profound. Photosynthesis on Earth is tuned to the solar spectrum that has been stable over geological time. Plants and algae use chlorophyll as the primary pigment, with strong absorption in the blue and red, and weaker absorption in green, which is why many leaves appear green. But chlorophyll is not the only pigment. Accessory pigments broaden the absorption range. The reason chlorophyll absorbs in blue and red, rather than green, is not an arbitrary preference for those colors. It is a consequence of molecular energy levels and the way those pigments evolved under the spectral distribution of sunlight and the transmission properties of water. In a red-shifted solar spectrum, blue photons would be rarer. Red photons would be abundant but lower in energy per photon. Photosynthesis depends on the energy of absorbed photons to drive electron transfer and ultimately to fix carbon. The basic chemistry of oxygenic photosynthesis requires enough energy to split water and produce oxygen, which is energetically demanding. On Earth, the process uses two photosystems in series, absorbing photons at around 680 and 700 nanometers. This clever arrangement makes use of red light efficiently. But if the available light were shifted further into the infrared, beyond about 700 to 750 nanometers, the photon energy drops, and more photons would be required per fixed carbon, or the chemistry would need to change. Under a cooler, redder sun with the same total energy, there will be more photons overall for a given energy flux, because each photon carries less energy. That might sound beneficial for photosynthesis if pigments can capture them, but pigments must match photon energies to their electronic transitions. Capturing longer wavelengths often requires different pigment molecules with smaller energy gaps. Some bacteria on Earth already use bacteria chlorophylls that absorb in the near-infrared. In a redder world, photosynthetic organisms might evolve pigments shifted toward longer wavelengths, perhaps making landscapes appear darker, even blackish, because organisms would absorb much of the visible and near-infrared to maximize energy capture. Leaves might not be green. They could be deep purple, brown, or nearly black, depending on how pigments and protective compounds balance energy capture and photo damage. Photo damage itself would change. With fewer blue and ultraviolet photons, there would be less high-energy radiation to cause DNA damage and to drive photochemical reactions in the atmosphere. Ozone formation depends on ultraviolet photons breaking oxygen molecules, creating free oxygen atoms that combine with O2 to form O3. If ultraviolet output is reduced, ozone production could decline. But ozone destruction also depends on ultraviolet. The net result would depend on the detailed UV spectrum. A cooler star emits less UV overall, so the stratospheric ozone layer might be thinner. Paradoxically, surface UV might still be low because the source is weak, but the protective chemistry could differ. The atmosphere's temperature structure would also shift because ozone absorbs UV and heats the stratosphere. With less UV heating, the stratosphere might cool, altering circulation patterns. Circadian rhythms are another deep coupling. Many organisms use blue light to entrain biological clocks. In humans, specialized retinal ganglion cells contain melanopsin, most sensitive to blue cyan light around 480 nanometers. This system regulates sleep-wake cycles and hormone release. Under a redder sun with less blue content, circadian entrainment might weaken or shift. Organisms could evolve different photoreceptors tuned to available wavelengths, perhaps shifting sensitivity toward green or even red. But red light penetrates tissue differently and may interact differently with biology. The evolution of visual systems could drift toward longer wavelengths, perhaps making trichromacy shift or even making tetrachromacy more advantageous if the spectrum has distinct features. Vision itself depends on the spectrum, not only for color, but for focus. The eye's lens is chromatic aberration. Different wavelengths focus at slightly different depths. Under a spectrum dominated by longer wavelengths, the balance of optical design might shift. The scattering in the eye's media depends on wavelength too, with shorter wavelengths scattering more. With less blue, visual clarity and haze might improve. But the sky's illumination would be different. affecting contrast and the appearance of shadows. Materials that rely on fluorescence, absorbing UV and emitting visible light, would behave differently. Many whites in modern fabrics and papers are whitened with optical brighteners that fluoresce under UV, emitting blue light to counter yellowing. Under a sun with less UV, those materials would look duller and more yellowish, even if the material itself is the same, because the fluorescence would be missing. Climate under a redder sun would not only be about total energy, it would be about where the energy is absorbed. Water vapor, carbon dioxide, and methane have absorption bands primarily in the infrared. A redder star emits more of its energy in the near-infrared, which will be absorbed more strongly by atmospheric water vapor and CO2 before reaching the surface. That would increase atmospheric heating relative to surface heating, potentially altering convection and cloud formation. It could make the greenhouse effect more efficient for the same total incoming energy, because more incoming radiation is in wavelengths that interact with greenhouse gases. On the other hand, ice and snow reflect visible light strongly, but absorb more in the near-infrared. Under a redder spectrum, ice would absorb more energy and reflect less. That reduces the stabilizing power of ice albedo feedback in a familiar way and might make ice less reflective, warming the planet relative to what one would expect from total insolation alone. This could partially compensate for lower luminosity if luminosity were not held fixed, but it could also destabilize climate if luminosity were held fixed, making polar ice less resilient. Now move in the other direction. A blue sun suggests a hotter star, emitting more short-wavelength light. A black body at 8,000 to 10,000 Kelvin has a spectrum weighted toward the blue and ultraviolet. If the sun's radius stayed the same and temperature rose, luminosity would increase dramatically, baking Earth. To keep insolation constant at Earth, the star's radius would need to decrease. A hotter star with the same luminosity would be smaller. Radius scales as T_current/T_nu, caret 2. At 9,000 Kelvin, radius would be about 5770/9000. Caret 2 is almost equal to 0.41 of the sun's radius. That would be a different star in mass and structure, perhaps not stable in the same way. But again, as a definable scenario, Earth receiving the same total energy but with a bluer spectral distribution. It is coherent enough to explore. Under a bluer sun, the sky could be intensely blue, perhaps even trending toward violet if enough short-wavelength visible light exists. Rayleigh scattering would be very effective, and the diffuse skylight might dominate. Shadows might appear deeper and cooler in tone because the scattered light filling them would be rich in blue. The sun's disk might appear whiter but with a harsh, high-contrast quality because there will be more short-wavelength light that scatters and causes glare. Human eyes are less sensitive in the violet, and the lens absorbs some UV, but strong blue and near UV content would alter visual comfort. The risk of retinal photochemical damage increases with blue light exposure. Modern discussions of blue light hazard are modest compared to what might exist under a truly hotter solar spectrum. The atmosphere's chemistry would shift markedly. More UV photons would increase the production of ozone and also drive photolysis of many gases. The stratosphere would heat more due to ozone absorption, potentially strengthening the temperature inversion that defines it. Higher UV can also break apart water vapor in the upper atmosphere, producing hydrogen that can escape to space over geological time. That can contribute to the loss of water and the oxidation of the planet. Under a blue sun, even with the same total energy at Earth, the fraction of energy in UV could be higher, increasing potential for atmospheric escape processes and altering long-term habitability. At the surface, life would need more robust UV protection. DNA absorbs strongly into UV, and UV-induced mutations can be lethal or carcinogenic. Many organisms use protective pigments, DNA repair mechanisms, and behaviors to avoid UV. Under a high UV star, these will become more critical. Plants might evolve thicker cuticles, more UV-absorbing compounds like flavonoids, and perhaps different leaf structures to manage photon load. The ocean might become a more important refuge because water absorbs UV strongly, especially at shorter wavelengths. Marine ecosystems might concentrate deeper, changing the vertical structure of photosynthesis and nutrient cycling. Photosynthesis under a bluer spectrum has the advantage of higher energy photons, but Too much energy can be damaging. Photosystems can be overloaded, producing reactive oxygen species that harm cells. Plants already manage excess light with non-photochemical quenching, dissipating energy as heat. Under a bluer sun, these protective systems would be under greater selection pressure. Pigments might shift to absorb more in the blue, and perhaps reflect more in the green and red to avoid overheating. Landscapes might appear more reflective, perhaps more silvered, because organisms would benefit from reflecting excess energy. Deserts might become brighter. Snow and ice already reflect strongly and visible in UV, but they can absorb some UV too. Under a bluer sun, the reflectance properties of surfaces would change their energy balances in complex ways. The climate response would also shift because a larger fraction of incoming energy would be at wavelengths not strongly absorbed by greenhouse gases, at least in the visible. More energy would reach the surface directly rather than being absorbed in the atmosphere. That could increase surface heating and convection, potentially increasing cloud formation. Clouds reflect visible light strongly. Under a bluer spectrum, cloud albedo might increase, reflecting more incoming energy and providing a stabilizing feedback. But clouds also interact with long-wave infrared outgoing radiation, trapping heat. The net effect depends on cloud type, altitude, and droplet size. Spectral changes could alter cloud microphysics because photochemistry influences aerosols that act as cloud condensation nuclei. A more UV-rich atmosphere can produce different oxidants and change aerosol formation, which changes cloud properties and thus climate. Daylight quality under a bluer sun would change the appearance of materials. Many materials that appear warm under current sunlight might look cooler. Skin tones might shift, what might look more desaturated. The world might take on a slightly clinical feel, not because it is less beautiful, but because the spectral balance that our visual system is calibrated to would be different. Color constancy might partly compensate, but the highlights and fluorescence would change. Some minerals fluoresce under UV, producing visible light. Under a more UV-rich sun, fluorescence in rocks, sands, and biological materials could be more noticeable, especially in shaded areas where UV still penetrates and emitted visible light stands out. Now consider the most perplexing idea: a green Sunday. For a star to appear green in the way a laser appears green, it would have to emit predominantly in a narrow green band with little red or blue. Thermal emitters do not do that. A black-body spectrum always spans both sides of the peak. Even if the peak is in the green, the red and blue tails are present. To create a truly green-appearing sun, one needs either a filtering process that removes most red and blue from the beam, or a star whose photosphere emits unusually in green due to some exotic, non-thermal emission, which would be unlike normal stars. In a physically honest narrative, the green sun becomes a scenario about filtering. Filtering can happen in Earth's atmosphere or in space. Suppose an orbital filter, perhaps a vast engineered structure, selectively blocks red and blue wavelengths while transmitting green. The total power reaching Earth could be adjusted to match current levels, but the spectrum would be narrow. Under such illumination, the world's colors would collapse. Objects that reflect green would appear bright. Objects that reflect primarily red or blue would look dark. The sky's scattered light would still be greenish because Rayleigh scattering would scatter the transmitted green. The sky might be a luminous, eerie green dome, not supernatural, but simply the consequence of monochromatic illumination. Under monochromatic light, color vision loses its purpose. The cones would be stimulated in a pattern determined largely by the single wavelength, and differences between objects will be mostly in brightness, not hue. Many animals would evolve away from color discrimination toward higher contrast sensitivity, perhaps resembling monochromatic vision systems. But biology could also exploit polarization and spectral edges if the filter is not perfectly narrow. Some insects on Earth already use polarization patterns in the sky for navigation. Under a green-dominated sky, polarization might remain and could become even more central. Photosynthesis under narrowband green would be challenging. Chlorophyll reflects green relatively strongly, which is why leaves look green under broadband sunlight. But chlorophyll does absorb some green. It is not a perfect reflector. Still, if the available photons were mostly green, organisms would be under pressure to evolve pigments that absorb green efficiently. This could drive a shift in pigment chemistry. Instead of green reflection, leaves might become dark, absorbing green. The world could become visually darker despite bright light, because organisms would capture most of the available photons. The atmosphere's chemistry would also shift because UV would be reduced if the filter blocks it. Ozone formation would decline. Vitamin D synthesis in human skin requires UVB light. Under a green-only spectrum, vitamin D deficiency will become universal unless dietary sources compensate. This would ripple into calcium metabolism and skeletal health. Over evolutionary timescales, organisms might evolve alternative pathways or rely on diet and microbiomes. Human-like physiology might not arise in the same way. Technology would change sharply. Solar panels rely on photons with energies above the semiconductor band gap. Silicon has a band gap corresponding to about 1.1 electron volts, which means it can absorb photons with wavelengths shorter than about 1,100 nanometers, spanning visible and near-infrared. Under green, only light around 530 nanometers. Silicon panels would work because photon energy is efficient, but the efficiency would depend on spectral match. Many solar technologies are optimized for the full solar spectrum, and narrowband illumination would create different thermal and electrical behaviors. Lighting, photography, and art would be fundamentally different. Under green illumination, pigments would not display their intended colors. Human culture, if it developed, would build color language differently, perhaps emphasizing texture, reflectivity, and luminosity rather than hue categories. A violet sun is, in physics terms, a sun with even more short-wavelength output, edging toward ultraviolet dominance. In practice, a truly violet star would be very hot, and in visible light it might actually appear blue-white, because human eyes are less sensitive in the violet. But if enough violet and near UV were present, the sky might take on a deeper indigo. The hazards of biology would intensify. DNA damage, protein denaturation, and oxidative stress would be major constraints. Protective pigments like melanin absorb across UV and visible. Many organisms would likely be darkly pigmented, perhaps even black, to protect against intense UV. But dark surfaces absorb heat. Under constant total energy, more UV could mean less infrared warmth. Yet UV absorbed at the surface could still heat. The balance between heating and damage would shape morphology. Life might prefer shaded microhabitats, under canopies within soil or underwater. Under a red sun, the opposite might occur. UV would be lower. Organisms might be less pigmented, perhaps more translucent. But then other constraints appear. With less UV, some photochemical pathways used by organisms would be weaker. Plants use blue light receptors for phototropism, stomatal opening, and developmental cues. A shift in spectrum would reshape plant form. Leaves might be larger to capture more light if total visible flux is lower. But if total energy is held constant and is shifted to longer wavelengths, leaves might need to manage heat differently, because near-infrared is absorbed strongly by water. Many leaves reflect near-infrared to avoid overheating. That is why vegetation has a strong red edge in reflectance, a sharp increase in reflectance just beyond 700 nanometers. Under a redder star, the incentive to reflect near-infrared might increase, making vegetation even more reflective in that band. This would influence remote sensing and climate, because surface albedo in near-infrared would change. Remote sensing itself is a clue to how astronomers would interpret such worlds. Astronomers measure stellar colors using photometric filters, comparing brightness in different bands to obtain color indices like BV. A star's color index correlates with temperature. The sun's BV is about 0.65, corresponding to a G-type star. A redder sun would have a larger BV, perhaps corresponding to a K-type star. A bluer sun would have a smaller BV, corresponding to an F-type or A-type star. These classifications are not cosmetic. They tie to mass, lifetime, and activity. Hotter, more massive stars live shorter lives. Cooler, less massive stars live longer. But in our earlier luminosity-compensated scenarios, we change radius dramatically to keep luminosity constant at Earth, which can decouple some intuitive expectations. In real stellar physics, temperature, radius, luminosity, and mass are linked by stellar structure equations. A star with the sun's luminosity but much higher temperature would generally have a different mass and internal fusion rate. It might not be stable for billions of years. That matters for life, because complex life on Earth took a long time to evolve. Still, the exercise is not to build a perfect stellar evolution model. It is to explore what spectral distribution does to a planet, holding as much else fixed as possible and acknowledging when that is artificial. The honest approach is to define a coherent scenario and follow its consequences, while noting where the scenario departs from what an actual star would likely be. A different route to colored sun is not to change the star's temperature drastically, but to change its spectral filtering via its atmosphere. The sun has a photosphere, and above it the chromosphere and corona. The photosphere emits a continuum. The upper layers can absorb and emit specific lines. If the opacity in certain bands change, perhaps due to different abundances of elements or different temperature gradients, the spectrum could be reshaped. This could, in principle, shift the apparent color slightly without huge changes in total luminosity. For example, stronger absorption in the blue could make the sun appear warmer. Stronger absorption in the red could make it appear cooler. But the effect would be modest. It would not create a pure green or pure blue sun. Earth's atmosphere is the more powerful filter for perceived color. The sun at noon overhead could be close to white, but near sunrise it is orange-red. That is purely geometry and scattering. If Earth's atmosphere were thicker, the sun could appear more reddened even at midday. If it were thinner, the sun could appear whiter and the sky darker, perhaps a deeper blue. If the atmosphere had different composition, such as more methane haze like Titan, the sunlight could be filtered to a more orange tone. A world under an orange sky could exist with the same sun, just a different atmosphere. But the topic here remains fixed, the sun in other colors. Even if the star is unchanged, the sun as seen is a product of spectrum plus filtering. And in daily experience, the color of the sun is the color of the light that reaches the observer. So the meaning of sun color must always include both physics and perception. A star emits a spectrum. A medium modifies it. A visual system maps it. When any of these changes, the sun can be said to be a different color. The consequences then cascade. Begin with the most intimate interface, the retina. Under current sunlight, the visual system operates in photopic conditions, using cones for color vision. In dim light, rods dominate, providing monochrome sensitivity with a peak around 507 nanometers in the blue-green. This is why nighttime scenes appear bluish and why red objects look darker at dusk. The Purkinje shift. If the sun were redder and the spectrum had less blue-green, then rods would be less stimulated at low light, potentially making twilight and shaded conditions seem darker. Night vision might evolve differently, perhaps shifting rod sensitivity toward longer wavelengths, but that would require different photopigments. Evolution can do that. Some animals already have rod sensitivities shifted. Deep-sea fish have visual pigments tuned to the blue light that penetrates water. In a red sun world, if the ambient light is redder, pigments might shift. But the eye is not just a sensor. It is also a device designed around the environment spectrum. The lens transmits visible light, but absorbs much ultraviolet. In humans, the lens yellows with age, filtering blue light. Under a blue sun, such filtering might be advantageous earlier, protecting the retina. Under a red sun, the lens might remain clearer, and the eye might evolve to transmit more near-infrared if it provides useful information. Yet near-infrared photons are less energetic and typically not detected by human photopigments. To see in near-infrared, pigments would need different energy transitions. Some animals can detect near-infrared indirectly via thermal sensing, but that is different from vision. The perception of color categories is also shaped by illumination. Under narrowband illumination, the world loses hue variety. Under broad but shifted illumination, the world retains variety but the balance changes. The brain's color constancy might adapt over development, leading to a new white point. Under a red sun, what counts as white might be warmer. Under a blue sun, white might be cooler. But there are limits because color constancy relies on assumptions about the illumination spectrum and the statistics of natural scenes. If the illumination spectrum lacks certain wavelengths, no amount of neural compensation can recover them. A red sun with very little blue would make it impossible for objects to reflect blue light into the eye. Blues would become muted. The world would have fewer saturated blues. The ocean might not look blue, because its blueness is partly due to scattering and absorption properties that favor blue return under broadband light. Under red illumination, the ocean would look darker, perhaps gray-green or even black in deeper water, with reddish highlights in shallow areas where sediment and reflection return. This shifts culture indirectly, but culture is a downstream consequence. The primary is physics. What happens to energy flow? Solar energy drives Earth's climate by heating the surface and atmosphere. Incoming solar radiation is mostly in the visible and near-infrared. Outgoing thermal radiation from Earth is in the mid-infrared, around 10 micrometers, much longer wavelengths. The greenhouse effect arises because gases like water vapor and CO2 absorb outgoing infrared, reducing the rate of cooling, raising surface temperature until energy balance is restored. If the sun spectrum shifts towards shorter wavelengths, more energy arrives in bands where the atmosphere is transparent and reaches the surface, increasing surface heating and convection. If it shifts toward longer wavelengths, more energy is absorbed by water vapor and CO2 in the atmosphere, potentially warming the atmosphere and changing lapse rates. These changes can alter the vertical temperature profile, which affects stability, cloud formation, and precipitation patterns. Climate is not just about mean temperature. It is about circulation. Albedo, the reflectivity of a surface, is wavelength dependent. Snow and ice reflect visible light strongly, giving high albedo under current sunlight. But in near-infrared, snow and ice absorb more. Oceans absorb strongly in the red and infrared, reflecting and scattering more in blue. Vegetation reflects strongly in near-infrared and absorbs in visible. Deserts have their own spectral signatures. Under a red sun, with more near-infrared, snow would be less reflective and thus warmer. Under a blue sun, snow might reflect even more of the incoming energy if more energy lies in visible blue bands, potentially cooling. But UV can be absorbed by snow too, and photochemistry can alter snow's surface. The net effect depends on the detailed spectrum. Consider also atmospheric scattering and absorption. Shorter wavelengths scatter more, increasing diffuse radiation. Diffuse radiation can penetrate deeper into plant canopies in direct sunlight, increasing photosynthesis in shaded leaves. There's a known phenomenon on Earth. After volcanic eruptions, increased aerosols scatter sunlight, increasing the diffuse fraction and sometimes enhancing plant productivity despite reduced total sunlight. Under a blue sun with more scattering, diffuse light might be enhanced, changing forest structure and productivity. Under a red sun with less scattering, direct beam might dominate, increasing contrast and perhaps making shaded understories less productive. Water vapor absorbs in near-infrared. Under a redder spectrum, more incoming energy might be absorbed in the lower atmosphere, heating it and potentially increasing evaporation. Increased evaporation increases water vapor, which is itself a greenhouse gas, creating feedback. But if the spectrum is redder because the star is cooler and has less total UV, the stratosphere might be cooler and drier, affecting water loss. These interactions are subtle. The atmosphere is a coupled dynamical chemical system. Now bring in the chemistry of the upper atmosphere. Under a blue or violet sun with more UV, photolysis rates increase. More ozone forms. Ozone absorbs UV and heats the stratosphere. A warmer stratosphere changes the tropopaus's height, the propagation of planetary waves, and the distribution of jets. It also affects how the atmosphere circulates trace gases. More UV also increases the formation of hydroxyl radicals, which are the atmosphere's cleansing agents, oxidizing methane and other compounds. That changes greenhouse gas lifetimes. A planet under a more UV-rich star could have lower methane levels because methane is destroyed faster, reducing greenhouse warming, potentially offsetting other effects. Under a redder star, with less UV, methane could persist longer, potentially building up, increasing greenhouse warming. This is one reason why planets around cooler stars might have different atmospheric compositions. The stellar spectrum shapes atmospheric photochemistry. The sun and other colors would thus shape not only climate directly through heating, but indirectly through atmospheric composition. All of this feeds back into habitability. Astronomers define a habitable zone as the range of distances where a planet could have liquid water on its surface, given a certain atmosphere. But habitability depends on spectrum too. A redder star's light interacts differently with ice and greenhouse gases, shifting the inner and outer edges of the habitable zone. A planet could be habitable at a different distance if the spectrum is different, even if total luminosity is the same. In our thought experiment, Earth stays at $1 Australian, but the rules that define its climate shift. Now consider the sun's activity, flares, coronal mass ejections, and the solar wind. These phenomena are tied to magnetic fields and plasma physics, not directly to visible color. But the spectrum matters insofar as activity changes the UV and X-ray output. The sun's high-energy emissions come largely from the hot corona, millions of Kelvin, emitting in extreme ultraviolet and X-rays. If the sun were a different kind of star, its magnetic activity might differ. Cooler stars can be more active in flares relative to their luminosity, and hotter stars have different wind properties. But to stay anchored, focus on how the spectral distribution affects technology and biology. Satellites rely on solar panels, which converts sunlight to electricity. The power output depends on both total irradiance and spectral match to the panel's band gap. Many satellites also rely on thermal design. They absorb and emit radiation, balancing heat. A redder spectrum might heat surfaces differently because coatings have wavelength-dependent absorptivity. Thermal blankets, paints, and radiators are designed around the solar spectrum. A shifted spectrum can make some surfaces absorb more and overheat, while others reflect more and become colder. Spacecraft could require different materials. On Earth, photovoltaic technology would shift. Silicon panels respond well to visible and near-infrared up to about 1,100 nanometers. Under a redder sun, with more near-infrared, silicon could still perform well, potentially even better if the spectrum matches its absorption, but thermal losses might increase. Under a bluer sun, more photons are above the band gap and can be absorbed, but excess photon energy above the band gap is lost as heat in the semiconductor, a process called thermalization. This can reduce efficiency gains from higher energy photons. Multi-junction solar cells, which stack materials with different band gaps, can capture different parts of the spectrum more efficiently. Under a different sun, optimal designs would shift. A violet sun might favor wide bandgap materials that can capture high-energy photons without as much thermalization loss, while a red sun might favor narrower bandgaps that can capture longer wavelengths. Materials degradation is sensitive to UV. Many polymers, paints, and coatings break down under UV exposure, becoming brittle and yellowed. Under a UV-rich sun, infrastructure would age faster. Outdoor materials would require UV stabilizers or different chemistries. Under a UV-poor red sun, materials might last longer, but microbial growth and photodegradation processes would shift. Photocatalysis, used in some self-cleaning surfaces, relies on UV. It might not work as well. Aviation and radiation exposure depend on cosmic rays and solar energetic particles, but UV spectrum also matters for the atmosphere's shielding and for ozone. A stronger ozone layer under a UV-rich sun might protect against UV, but it could also change atmospheric density profiles, affecting flight conditions indirectly. But the direct link remains photochemistry. Now return to the lived experience of daylight. Under current sunlight, the sky is blue, and the sun is a bright white-yellow disk. Shadows are filled with blue skylight. Photographers talk about golden hour and blue hour, times when the spectrum of illumination shifts due to path length and scattering. In a world with a red sun, the entire day might resemble an extended golden hour, with warmer light even at noon. The sky could be paler, perhaps tending toward a washed-out blue-gray. Under a blue sun, midday might be harsh and cold, with an intensely saturated sky and high contrast. The sunsets could be even more dramatic, because the starting spectrum contains more short wavelengths to be scattered away, leaving the low sunbeam extremely reddened. But if the atmosphere's chemistry changes too, aerosols and ozone could change sunset colors further. Colors of objects would shift. Under a red sun, Green plants might appear different. Chlorophyll reflects green under current illumination partly because green is abundant and because the pigment does not absorb it strongly under redder light. Less green is present to reflect, so leaves might look darker, perhaps more olive or brown. Flowers that rely on pollinators with color vision would evolve different signals. Many insects see into ultraviolet. Under a red sun with less UV, UV patterns on flowers might be less useful. Pollination strategies could change, possibly favoring scent and shape over UV guides. Under a blue sun with more UV, UV patterns might become more important, and flowers might evolve strong UV reflectance or absorption patterns. This would alter ecology. Ocean ecology depends on light penetration. Blue light penetrates water deeper than red. Under a redder sun, the surface ocean would receive more red and near infrared, which water absorbs strongly. Light would be absorbed in a thinner surface layer, heating it more and reducing penetration to depth. This could stratify the ocean, reducing mixing and affecting nutrient transport. Phytoplankton might be confined to a shallower layer, potentially increasing surface productivity, but reducing deep photosynthesis. Under a bluer sun, more blue light penetrates deeper, potentially extending the photic zone, affecting deep water ecosystems and carbon cycling. The distribution of heating in the ocean matters for climate. If more energy is absorbed near the surface, the ocean's surface warms, potentially increasing evaporation and strengthening the hydrological cycle. But stronger stratification can reduce upwelling, starving surface waters of nutrients, reducing productivity, and altering carbon sequestration. These are not small effects. Over millions of years, they can reshape atmospheric composition through the carbon cycle. Now consider geology and the long arc of Earth history. The sun has brightened slowly over time as it converts hydrogen to helium in its core, increasing mean molecular weight and core temperature, raising luminosity. Early Earth faced a faint young sun problem. The sun's luminosity was lower, yet geological evidence suggests liquid water existed. Greenhouse gases likely compensated. If the sun were redder or bluer, the balance of greenhouse compensation would differ. A redder spectrum might enhance greenhouse absorption and reduce ice albedo, potentially making it easier to keep early Earth warm. A bluer spectrum might increase ice reflectivity and reduce greenhouse coupling, potentially making early Earth colder unless greenhouse gases were higher. Over time, feedbacks between life and atmosphere would respond. Life also shapes the atmosphere's optical properties. Oxygen produced by photosynthesis leads to ozone, which affects UV. Aerosols produced by biology affect scattering. If the sun spectrum changes, life's influence on atmosphere might shift. Under a red sun, perhaps methane persists longer, leading to a hazier atmosphere, which further reddens sunlight. Under a blue sun, perhaps oxygens reduce haze, making the sky clearer and bluer. These feedback loops could lock in different regimes. Human technology and culture, if they arose, would be shaped by daylight. Architecture would respond to different glare and heat. Under a blue sun, UV and glare might favor shaded streets and deep overhangs. Under a red sun, daylight might feel softer, encouraging open designs. Art would evolve under different illumination. Pigments would be chosen for how they reflect the available wavelengths. The concept of warm and cool colors could be anchored differently. But even without cultural speculation, the engineering consequences are concrete. Lighting design, imaging sensors, and energy systems will be optimized to the spectrum. Cameras and sensors are calibrated to the solar spectrum. White balance settings assume typical daylight, tungsten, fluorescent, and so on. Under a different sun, the baseline daylight would shift. Colorimetry, the science of measuring and reproducing color, is defined relative to standard illuminance based on typical daylight spectra. A red sun would redefine those standards. The CIE color space is built around human vision under certain illuminance. Under different spectral distributions, the mapping between spectra and perceived colors would change. Now consider a different approach. Keep the sun's effective temperature the same, but make it appear different colors by altering Earth's atmosphere. A thicker atmosphere with more Rayleigh scattering would make the sky more intensely blue and the sun more reddened at all times. A thinner atmosphere would make the sky darker and the sun whiter. Add aerosols that absorb blue, and the sun could appear redder. Add aerosols that absorb red, and it could appear bluer in extreme cases. But these scenarios are about atmospheric optics, rather than changing the star. Still, the consequences are real. A world with a red sun, due to haze, would have reduced photosynthetically active radiation in blue and maybe in UV. It would be like permanent smoky conditions. Plant growth would adapt. Human health would change due to less UV and different air quality. But since the topic is the sun in other colors, it is valid to treat this as the sun's perceived color, with physical consequences due to filtering. Yet the most instructive scenarios are those where the source spectrum changes, because they reveal how deeply life is tuned to photon energies. To keep the exploration grounded, consider for archetypal spectra, a red-shifted spectrum. Peaking at longer wavelengths would reduce blue and UV. A blue-shifted spectrum. Peaking at shorter wavelengths would increase blue and UV. A narrow-band green-dominated spectrum created by filtering. A spectrum with enhanced ultraviolet relative to visible, a violet-leaning case. In each, keep returning to the same core ideas, each time deeper. Perception versus measurement, spectrum versus color name, atmosphere's filter, biology tuned to sunlight, climate tuned to spectral balance, and technology relying on solar behavior. Perception versus measurement begins with the sky itself. The sky is not blue because the sun is blue. It is blue because the atmosphere scatters blue. If the sun were redder, the sky could still be blue, but less intense because there is less blue to scatter. If the sun were bluer, the sky could become even more saturated. But also, the sky's color depends on ozone absorption in the Chapuis bands in the visible, which can subtly affect the spectrum of skylight, and on aerosols. Under a different UV output, ozone levels would change, altering the color of the sky. This is a second-order effect, but in a carefully reasoned world, second-order effects accumulate. The sun's disk color is also shaped by limb darkening. The sun is not equally bright across its disk. Toward the edge, the limb, we see higher, cooler layers, making it dimmer and slightly redder. Under a different temperature gradient or opacity, limb darkening would differ. The sun might have a different apparent limb hue. This would alter the aesthetic of the solar disk, but more importantly, it indicates that even the color of the sun is not uniform. Now return to blackbody radiation. A blackbody's color is determined by temperature, but the perceived color depends on intensity and adaptation. At low intensities, a 3000 Kelvin source looks warm orange. At high intensities, it can look nearly white because the visual system adapts. The sun is intensely bright, and direct viewing is impossible without damaging eyes. Perceived solar color is often inferred from indirect observation or filtered viewing. In a documentary sense, one can treat the sun's color as the color of daylight in shaded conditions because that is what shapes the world. Under a redder sun, shaded areas will be filled with redder diffuse light, altering perception. Under a bluer sun, shaded areas will be filled with bluer diffuse light. Consider also the difference between spectral power distribution and color temperature. Color temperature is a way to describe the color of a light source by the temperature of a blackbody that would produce similar perceived color. Many light sources are not true blackbodies. They have spikes and gaps. The sun is close to a blackbody, but the atmosphere modifies it. A red sun created by filtering could have a color temperature similar to a blackbody at lower temperature, but its spectrum could be missing particular bands. Biological and technological responses would depend on the actual spectrum, not merely the perceived color temperature. This matters for photosynthesis. Photosynthetically active radiation on Earth is often defined as 400 to 700 nanometers, the visible band used by many plants. But that definition is anthropocentric and Earth-specific. Under a red sun, organisms might use 700 to 900 nanometers more heavily, extending PAR into near-infrared. Under a blue sun, perhaps PAR shifts to include more near UV. But near UV can be damaging, so it might be used carefully, perhaps by organisms with robust protective structures. Pigments could evolve to absorb in different bands. The evolutionary landscape of pigments is constrained by chemistry. Molecules have energy level gaps. To absorb longer wavelengths, pigments need smaller gaps, which will make them more prone to thermal noise and less stable. To absorb shorter wavelengths, pigments need larger gaps, which will be more stable but require more energetic photons, increasing damage risk. In oxygenic photosynthesis, the energy needed to split water sets a lower bound on photon energy. The two-photosystem scheme is a clever workaround. Could be extended to longer wavelengths by adding more photosystems in series, each capturing lower energy photons and stepping up the energy in small increments? In principle, yes. Some theorists have proposed multi-photosystem chains for exoplanet photosynthesis under redder stars. But each additional photosystem adds complexity and potentially reduces efficiency due to losses. Under a red sun, life might still manage it, but the energy flow per photon would change, affecting the productivity of ecosystems. Productivity influences atmospheric oxygen. Earth's oxygen-rich atmosphere is a product of photosynthesis and burial of organic carbon. If productivity declines or shifts, oxygen levels could differ. Oxygen levels affect combustion, metabolism, and the evolution of large animals. Under a red sun with less UV and perhaps different photosynthesis efficiency, oxygen might be lower or higher depending on net productivity and burial. Under a blue sun with more UV, oxidative weathering and photochemical processes could differ, affecting oxygen stability. These are long timescale consequences. Now consider vitamin D synthesis. Human skin produces vitamin D when UVB photons convert 7-dehydrocholesterol to pre-vitamin D3. Under a red sun with less UVB, this pathway weakens. Populations would need dietary vitamin D, perhaps from fish or fortified foods, or evolution might favor lighter skin to maximize UV absorption. But if UV is low, even light skin might not suffice. Under a blue sun with more UVB, vitamin D synthesis could be abundant, but skin cancer risk increases, favoring darker pigmentation. The geographic distribution of skin pigmentation on Earth reflects a balance between vitamin D synthesis and UV protection. Under a different sun, this balance would shift, potentially changing the evolution of human-like traits. Circadian rhythms again. Melanopsin peaks around 480 nanometers. Under redder light, the signal could be weaker. Organisms might evolve photoreceptors tuned to other wavelengths. Plant circadian systems use phytochrome sensitive to red and far red light, and cryptochrome sensitive to blue. Under a red sun, phytochrome signaling might dominate. Under a blue sun, cryptochrome signaling might dominate. These shifts would change flowering times, growth patterns, and seasonal behaviors. Now shift to the atmosphere's interaction with different spectra. Ozone absorbs UV and some visible. Water vapor absorbs near-infrared. CO2 absorbs near-infrared and infrared. Methane absorbs in near-infrared too. Under a red sun with more near-infrared, greenhouse gases will absorb more of the incoming radiation, heating the atmosphere higher up. This could reduce the amount of energy reaching the surface, potentially cooling the surface while warming the atmosphere, changing convection. But surface temperature is what matters for habitability, and the surface also receives energy via downwelling infrared from the atmosphere. The net could be warming or cooling, depending on the vertical distribution. Under a blue sun, incoming radiation might pass through more cleanly, heating the surface, increasing evaporation, increasing water vapor, increasing greenhouse effect. But increased clouds could reflect incoming radiation. The climate might find a new equilibrium. Now consider the color of the sun as seen at different times. Under a red sun, sunrise and sunset might be less distinct in color shift because the spectrum already lacks blue. The additional scattering might not change perceived color as dramatically. The sky could remain relatively pale. Under a blue sun, sunrise and sunset could be spectacularly red because a path length removes more blue from an already blue-rich beam, leaving a strongly reddened remainder. But the atmosphere has more ozone due to UV. Ozone's absorption can produce deeper reds and purples. Aerosols from increased photochemistry could also alter colors. All of these affect human perception and art, but again, the anchor is physics. Now, take a deeper pass into radiative transfer. Light traveling through a medium is attenuated by absorption and scattering. The beer, Lambert law describes exponential attenuation with optical depth. Optical depth depends on wavelength. For Rayleigh scattering, optical depth increases sharply for shorter wavelengths. For aerosols, the dependence is weaker and depends on particle size distribution. For absorption, specific molecules have specific cross-sections at specific wavelengths. The atmosphere's transmission spectrum has windows and bands. The visible window exists because nitrogen and oxygen do not absorb strongly in visible. Water vapor and CO2 absorb more in infrared. Ozone absorbs in UV. If the sun spectrum shifts into bands where the atmosphere absorbs, then the effective solar constant at the surface changes even if the top of atmosphere radiance is the same. A red sun with more near-infrared might lose more energy to atmospheric absorption before reaching the ground, altering surface climate. A blue sun with more UV might have much of that UV absorbed in the stratosphere by ozone, heating high altitudes and reducing surface UV somewhat, but still leaving more UV than today. Atmospheric scattering also affects how energy is distributed spatially. Diffuse light arrives in the whole sky dome, reducing directional intensity. This affects plant canopy light distribution and also affects thermal comfort. Under more diffuse light, surfaces heat more evenly. Under more direct light, surfaces facing the sun heat more. Now consider the sun's influence on the ionosphere. The ionosphere is created by solar UV and X-rays ionizing atmospheric gases. It affects radio propagation. If the sun were bluer and more UV-rich, the ionosphere could be more ionized, affecting HF radio. If the sun were redder and UV-poor, the ionosphere could be weaker, changing long-distance radio propagation. This is a direct link between spectrum and technology. GPS signals pass through the ionosphere, and ionospheric delays depend on electron content. A different UV spectrum could change typical electron densities, affecting navigation systems. Power grids are affected by geomagnetic storms, which are tied to solar activity, but the ionospheric conductivity also matters. A different spectral output might shift baseline ionospheric behavior. Auroras are produced by charged particles, but their colors are determined by the emission lines of oxygen and nitrogen in the atmosphere. The sun spectrum does not directly change aurora colors, but it can change the ionosphere and thermosphere temperature and composition, potentially affecting auroral altitude and brightness. Under a more UV-rich sun, the upper atmosphere could be hotter and more expanded, affecting satellite drag. This is a technological consequence of spectrum. UV heats the thermosphere. Even if total solar energy is constant, increased UV fraction can increase thermospheric heating because UV is absorbed efficiently high up. Satellites would experience more drag. Low Earth orbit would be less stable. This is a concrete engineering change. Under a red sun with less UV, the thermosphere might be cooler and less expanded, reducing drag, making low Earth orbit more stable. But this is not free. Changes in ozone and stratospheric temperature could have other consequences. Now return to a green sun filter scenario and examine the atmospheric implications. If UV is blocked, ozone declines. Without ozone, the stratosphere's heating changes. The temperature profile could become more monotonically decreasing with height, changing stability. This could allow convection to reach higher, altering storm dynamics. The absence of UV also affects the production of certain aerosols and the breakdown of pollutants. The atmosphere could accumulate gases that are normally broken down by sunlight. The chemical steady state changes. If the filter blocks red and transmits green, the near-infrared is blocked, reducing heating of water vapor bands. That could cool the lower atmosphere relative to surface. But the surface receives green light, which is absorbed by many surfaces depending on reflectance. The overall heating pattern changes. A narrowband spectrum can lead to strange thermal behaviors because different materials absorb differently at that wavelength. Now consider human agriculture under different spectra. Plants have action spectra. Photosynthetic rate as a function of wavelength. Red and blue are generally most effective for many plants. Green is less effective but not useless. Green penetrates deeper into leaves and can contribute to photosynthesis in inner layers. Under a red sun with abundant red and far red, plants might adapt to use far red more, But far red also affects phytochrome signaling, which controls shade avoidance. Under more far red, plants might behave as if they are shaded, elongating stems and altering leaf angles, even in full sun. This could reshape plant architecture globally. Forests might become taller and more sparse, with different canopy structures. Under a blue sun with abundant blue, plants might be more compact with thicker leaves, because blue light promotes stomatal opening and regulates growth. Blue also affects phototropism strongly, leading to different leaf orientations. Crops could have different yields. The nutritional content of plants could change because pigment composition and protective compounds are influenced by light spectrum. For example, anthocyanins are produced under high light and UV stress. They are antioxidants. Under a blue sun, plants might produce more of these compounds, altering food chemistry. Under a red sun, perhaps less. Human mental health and neurobiology are influenced by light spectrum. Blue light suppresses melatonin. Under a red sun, melatonin suppression might be weaker, potentially leading to longer sleep or different circadian patterns. Under a blue sun, the opposite might occur. But again, in evolutionary timescales, physiology adapts. In shorter timescales, technology adapts. Artificial lighting could compensate, but the baseline environment would shape development. Now, deep in the physics of spectral distribution. The sun spectrum at Earth's orbit is often represented as AM0 in space and AM1.5 at the surface, where AM stand for air mass, a measure of path length through the atmosphere. AM1.5 is a standard for solar panel testing. The difference between AM0 and AM1.5 is a precise example of how the atmosphere reshapes spectrum. Under a different sun, those standards would change. The relative proportion of UV, visible, and IR would be different. The atmospheric absorption bands would carve different notches. The spectrum reaching the ground would determine not only color, but also heating. If the sun were cooler and redder, more of its emission would be in infrared bands that are strongly absorbed by water vapor, meaning the surface spectrum could be even more different from the top of atmosphere spectrum. This could reduce the visible brightness of daylight even if total energy remains high, because energy might be deposited as heat in the atmosphere rather than visible illumination at the surface. The world could be warm but dimmer with a hazy, diffuse glow. Conversely, under a bluer sun, more energy could arrive in visible bands, making daylight extremely bright even if total energy is unchanged, because less is absorbed in near-infrared bands before reaching the ground. This leads to a subtle distinction. Brightness and warmth can decouple. On Earth, sunny days feel warm and bright together because the spectrum includes both visible and near-infrared at warm surfaces. But if the spectrum shifts, the ratio of illuminance to heating changes. Under a bluer sun, there could be bright light with less infrared warmth, making daylight feel crisp but still energetically equivalent. Under a redder sun, there could be more infrared warmth with less visible brightness, making the world feel warmer but dimmer. Human perception might interpret this as a different kind of day, even at the same temperature. Illuminance, measured in lux, weights power by human visual sensitivity, which peaks around 555 nanometers in photopic vision. If the spectrum shifts away from that peak, the same physical power can produce less perceived brightness. A red sun that shifts power towards 700 to 900 nanometers would deliver energy that human eyes see poorly. The planet could receive plenty of energy but appear dimmer. Under a blue sun, if power shifts toward 450 to 500 nanometers, perceived brightness per watt might increase. This would alter the ecological importance of visual cues. Nocturnal and diurnal boundaries might shift. Now consider the role of the sun in defining the seasons. Seasons are set by axial tilt and orbital geometry, not by spectrum, but the response of ice and vegetation to seasons depends on spectrum. Under a red sun, ice melts more readily because it absorbs more near-infrared. Seasonal snow cover might be less stable, reducing seasonal albedo swings. Under a blue sun, snow is more reflective, potentially extending snow seasons. This would change seasonal temperature patterns and perhaps intensify or dampen seasonal contrasts. Now think about the hydrological cycle. Water evaporation depends on energy at the surface. If more energy is absorbed in the atmosphere, less reaches the surface, reducing evaporation. If more energy reaches the surface, evaporation increases. Under a red sun with more near-infrared absorbed by water vapor, surface energy might decrease unless compensated. But if total energy is held constant and if the atmosphere becomes more humid due to warming, absorption can increase further, reducing surface insolation and negative feedback. But higher atmospheric absorption also warms the atmosphere, increasing downwelling infrared, which can still heat the surface. The net effect could be a more humid, cloudy world with lower direct sunlight, but similar temperatures, perhaps a more diffuse, warm light. Under a blue sun, a clearer atmosphere might allow more direct sunlight, increasing evaporation, and perhaps producing different cloud regimes. But increased UV could also change cloud condensation nuclei, affecting cloud cover. Now consider ice and oceans again, but deeper. Ocean absorption of red light means that under a red sun, the ocean surface would heat more, increasing stratification, reducing mixing. This could reduce nutrient supply to surface phytoplankton, reducing carbon fixation, potentially increasing atmospheric CO2 over time, warming climate. But warming can increase weathering, drawing down CO2. The carbon cycle would find a new balance. Under a blue sun, deeper light penetration could allow photosynthesis deeper, potentially increasing carbon export to depth, reducing atmospheric CO2, cooling climate. But increased UV could damage phytoplankton at the surface, perhaps pushing them deeper. Now examine the appearance of the ocean. On Earth, the ocean looks blue because water absorbs red and scatters blue, and because the sky is blue and reflects. Under red light, the ocean could look dark because red is absorbed quickly and there is little blue to scatter. The surface might reflect a reddish sky, producing coppery highlights. Under blue light, the ocean could be intensely blue, perhaps even more luminous. This would affect navigation and perception. Now consider the appearance of human skin and other biological tissues. Skin has a reflectance spectrum shaped by melanin and hemoglobin. Hemoglobin absorbs in blue and green, reflecting red, giving blood its color. Under a red sun, skin might appear more uniform, with less contrast between oxygenated and deoxygenated blood because the illumination lacks blue-green that hemoglobin absorbs. Under a blue sun, blood's absorption could create stronger contrast, making veins appear differently. The appearance of bruises and rashes could change. Medical diagnostics that rely on color could change. Under a green-only sun, blood might appear very dark because green is absorbed, altering the appearance of injuries. These are subtle but real. Now think about vitamin A and vision pigments. Retinol, derived from vitamin A, is a chromophore in opsins. Its absorption can be tuned by the protein environment, shifting sensitivity. Under a different spectrum, selection would tune opsins. Some animals might evolve sensitivity into near UV under a blue sun, or into longer wavelengths under a red sun day. This would alter how the world is seen. Color categories would be different. Now think about plants again, but deeper into pigment evolution. Chlorophyll has absorption peaks around 430 and 662 nanometers. Chlorophyll B absorbs around 453 and 642 nanometers. Accessory pigments like carotenoids absorb in blue-green. These pigments evolved in a world where water filters light and where sunlight at the surface has a certain shape. In a red sun world, perhaps chlorophyll-like pigments shift to longer wavelengths. But longer wavelength pigments often have lower energy transitions, which can be more susceptible to thermal excitation, increasing noise. To maintain efficient charge separation, photosystems need a certain energy gap. This could limit how far into infrared oxygenic photosynthesis can go. This would constrain land productivity, perhaps limiting oxygen levels and thus limiting the evolution of large active animals. In contrast, under a blue sun, high-energy photons are abundant, but high-energy photons can damage photosystems. Organisms might evolve pigments that avoid absorbing too much UV, perhaps reflecting it. They might use sunscreen compounds. Leaves might appear different, perhaps more reflective and lighter in color, with a waxy sheen to reflect UV and blue. Forests might shimmer. Now consider the energy budget of leaves. Leaves absorb visible light for photosynthesis and reflect near-infrared to avoid heating. Under a red sun with more near-infrared, reflecting near-infrared becomes even more important. Leaves might evolve to reflect even more, increasing the planet's near-infrared albedo. This could cool the planet, a biospheric feedback. Under a blue sun, near-infrared is less significant, and leaves might not need as strong a red edge. Remote sensing of vegetation from space would look different. The vegetation red edge used to detect life on exoplanets might shift. Astronomers searching for biosignatures would need to consider the star spectrum. Now bring astronomy back in, carefully, only as it serves the topic. From afar, a planet around a redder star would reflect a different spectrum. The planet's color as seen by an astronomer depends on the star spectrum and the planet's albedo spectrum. A planet under a red sun might appear different in color indices. Its atmosphere might show different spectral features. Ozone features might be weaker. Methane features might be stronger. Vegetation reflectance edges might shift. These differences are not just curiosities. They determine detectability of life. Now consider the human experience of time. The sun spectrum influences the color of dawn and dusk, which are cues for timekeeping. Under a red sun, dawn might be less color shifting, perhaps more gradual. Under a blue sun, dawn might be more vivid. But timekeeping relies on intensity changes too, which depend on atmosphere scattering. Under a blue sun, scattering is stronger, so twilight might be brighter, extending the transition periods. Under a red sun, twilight could be darker and shorter. This affects daily rhythms. Now consider the impact on agriculture and energy capture. If daylight is dimmer and visible under a red sun, humans might rely more on artificial lighting for indoor activities. But if the sun provides the same total energy, there is still plenty of energy to harvest, perhaps more efficiently with infrared-optimized photovoltaics. Technology could adapt, but early in technological development, before advanced photovoltaics, reliance on direct sunlight for tasks could be different. But again, keep anchored. Spectrum affect perception and energy. Now consider the idea of a black sun or dark sun, which is not only allowed topic as a different color, but rather a different brightness. Avoid that. Stay with colors. Now consider the possibility of the sun that appears red not because it is cooler, but because its spectrum is filtered by its own atmosphere, perhaps due to heavy absorption in blue. In stars, metal lines can absorb in certain bands, but the sun's metallicity is fixed. To alter it significantly, you change composition. That implies a different star formation history. But as a thought experiment, suppose the sun's photospheric opacity increased in blue due to more line blanketing. This happens in metal-rich stars. Numerous lines in blue and UV absorb, redistributing energy toward longer wavelengths, making the star appear redder than a pure black body at the same temperature. This is a subtle but real astrophysical effect. A redder sun could be a sun with higher metallicity, causing more blue line blanketing. The total luminosity might remain similar, but the spectrum is redder. In that scenario, Earth would receive less UV and blue, more red. Many of the same biological and atmospheric consequences would occur, but less extreme than with a large temperature shift. Ozone might be lower. Vitamin D synthesis might be reduced. Photosynthesis might adapt. Climate might shift due to altered absorption. Similarly, a bluer sun could be a sun with lower metallicity, with fewer absorption lines in blue, allowing more blue and UV through. This could increase UV exposure and alter photochemistry without huge changes in luminosity. This is a physically plausible way to change color modestly, while keeping the star otherwise similar. It is also a reminder that color can be influenced by spectral lines and opacity, not only temperature. Now consider the solar spectrum's effect on human-made colorants. Pigments work by absorbing certain wavelengths and reflecting others. Under different illumination, pigments appear different. Some pigments rely on absorbing blue and reflecting red. Under a red sun, they might appear more saturated because the illumination is rich in red. Others rely on reflecting blue. Under a red sun, they would look dull. This would change the palette of art and design. But more importantly, it would change camouflage and signaling in nature. Many animals use color for mating and warning. Under a red sun, blue signals might be less visible. Under a blue sun, red signals might be less prominent if the illumination lacks deep red. Animals might evolve different coloration, perhaps structural colors that reflect the available wavelengths. Structural colors, like those in butterfly wings, arise from nanostructures that interfere with light, producing specific hues. Under different spectra, the evolutionary usefulness of certain structures changes. Now return to the sky and the scattering again, deeper. Rayleigh scattering depends not only on wavelength, but also on the refractive index and density of the atmosphere. Under a different sun spectrum, the atmosphere's temperature profile changes, affecting density. This can change scattering. Additionally, photochemistry affects aerosol production, affecting scattering. Under a UV-rich sun, more oxidants can produce more sulfate aerosols from volcanic sulfur, increasing haze. Under a UV-poor sun, aerosols might persist longer or shorter, depending on chemistry. These changes feed back into the sun's perceived color. The system is coupled. Now, consider the color of shadows. On Earth, shadows outdoors are not black. They're filled with blue skylight, making shadows bluish. Under a red sun with a pale sky, shadows might be less blue, perhaps more neutral or even slightly reddish if the sky's diffuse light is warm. Under a blue sun with an intense blue sky, shadows could be deeply blue. This changes visual contrast. Human architecture might use different materials to manage color cast. Photographic exposure would differ. Now consider human skin again, but in terms of thermoregulation. If the sun emits more near-infrared, skin absorbs and heats differently. Many fabrics reflect visible but absorb infrared differently. Clothing design would adapt. Under a red sun, fabrics might need to reflect near-infrared to stay cool. Under a blue sun, visible reflectance might matter more for comfort. Now consider the role of infrared in heating. Under a red sun, if more energy is in near-infrared, greenhouse absorption might intercept it, but surfaces also absorb near-infrared and heat. The net could be more warming of the lower atmosphere, possibly increasing humidity. Under high humidity, human comfort changes. Under a blue sun, perhaps drier conditions could prevail if photochemistry reduces methane and changes circulation. But these are speculative. Keep the chain. Spectrum changes absorption, changes heating, changes circulation. Now think about the long-term evolution of Earth's orbit and solar output. The sun brightens. If the sun were bluer, perhaps it would be hotter and evolve faster. The time scale for stable conditions might shorten. That matters for life. Under a redder, cooler star, stable conditions could last longer, but the spectrum might constrain oxygenic photosynthesis. This is a known tension in exoplanet habitability. M-dwarfs are cool and long-lived but have flares and emit in red and infrared, with less visible. Their planets receive different spectral distributions, but remain anchored. This is about our sun being different colors. Now return to the definition of color again, because it is the anchor. Color is a perceptual label for a spectral distribution within the sensitivity of the eye. It is not a single wavelength. A white light source is one that stimulates the three cone types in roughly balanced proportions. Many different spectra can appear white to humans. This is metamerism. Two spectra can look identical in color, while being physically different. This is crucial. A sun could appear the same color, while being physically different in spectrum. And the consequences for biology and climate could still differ, because biology and chemistry respond to photons differently than human cones do. A plant's action spectrum is not the same as human vision. Ozone formation responds to UV, which humans do not see. Therefore, describing the sun by a color name is dangerously incomplete. A sun that looks white could still be UV-rich or UV-poor. A sun that looks yellow could still have different near-infrared content. The world's climate and biology would respond to the full spectrum, not to perceived color. Therefore, when imagining other colors, it is more accurate to imagine other spectra, and then ask what color that spectrum would be perceived as by humans or by evolved eyes. Now deepen into photon energy. The energy of a photon is inversely proportional to wavelength. A 400 nanometer photon carries about 3.1 electron volts. A 700 nanometer photon carries about 1.8 electron volts. UVB photons around 300 nanometers carry about 4.1 electron volts, enough to break certain bonds and cause DNA damage. Infrared photons at 1000 nanometers carry about 1.24 electron volts. These differences matter. Chemical reactions have energy thresholds. Photosynthesis requires a certain energy. Photochemistry in the atmosphere requires photons above certain energies to break molecules. Under a red sun, fewer photons exceed those thresholds. Under a blue sun, more do. Now consider ozone again. O2 photolysis requires photons shorter than about 240 nanometers in the UVC, which is strongly absorbed by ozone itself and by oxygen. A hotter star emits more in this region, producing more ozone but also potentially more destruction. The balance yields a different ozone column. Ozone absorbs UVB and UVC, protecting the surface. Under a cooler star, ozone might be lower, but the star emits less UV, so surface UV might still be low. But if life produces oxygen, ozone might still form. The details matter. Now consider the role of UV in sterilizing the surface. UV can kill microbes. Under a blue sun with more UV, surface sterilization is stronger, perhaps reducing pathogen loads, but also making surface habitat harsh. Life might retreat to shaded or underwater environments. Under a red sun, UV sterilization is weaker, perhaps allowing more surface microbial life and faster decomposition, affecting carbon cycling. Now, consider the effect on mutation rates. UV increases mutation rates. Mutation rates influence evolution speed and cancer rates. Under a blue sun, mutation rates might be higher, potentially accelerating evolution but increasing individual risk. Organisms would evolve better DNA repair. Under a red sun, mutation rates might be lower, potentially slowing evolution or shifting to other mutagens. Now consider human technology again, particularly photochemistry used in industry. Many processes rely on UV curing, photolithography, and so on. Under a UV-rich sun, outdoor UV curing might be easier, but material degradation is worse. Under a UV-poor sun, UV-dependent processes will require artificial sources. Now consider agriculture and vitamin D again, but at societal scale. Under a red sun, vitamin D deficiency could be endemic unless diet provides it. Under a blue sun, skin cancer risk could be higher, requiring protective clothing and architecture. But these are downstream. Now consider color in astronomy. Stars are characterized by effective temperature and spectral class. The sun is a G2V star. If it were redder, it might be K-type. If bluer, F-type. The distribution of photons would shift. The habitable zone would shift. But since Earth stays at $1 the insolation may not match. If luminosity increases, Earth might become Venus-like. If decreases, Earth might become Mars-like. To keep Earth stable, we might adjust radius or distance, but the premise fixes Earth. Still, explore both. If sun changes color due to temperature change without compensating, Earth's climate becomes extreme, potentially freezing or overheating. That is a valid consequence. In a colder, redder sun without compensation, Earth would receive less energy and freeze. Ice would expand, increasing albedo, reflecting more sunlight, creating a runaway ice albedo feedback. The planet could become a snowball Earth with global ice cover. Under a red spectrum, ice reflects less, perhaps weakening the feedback, but the reduced luminosity would dominate. The atmosphere could collapse if CO2 freezes, but CO2 condenses at much lower temperatures. Water would freeze. Volcanic CO2 could accumulate because weathering slows under ice, eventually warming the planet and causing deglaciation. Snowball episodes occurred in Earth history. Under a redder, dimmer sun, snowball states might be more frequent or persistent. In a hotter, bluer sun without compensation, Earth would warm. Water vapor increases, enhancing greenhouse effect. Eventually, a moist greenhouse could occur, with water vapor reaching the stratosphere, photolized by UV, hydrogen escaping, drying the planet. With more UV, This could happen faster. The planet could lose oceans. This is a direct habitability limit. Thus, a bluer sun could shorten Earth's habitable lifetime. Now consider a moderate change, a slightly redder or bluer sun with the same luminosity. This could happen if metallicity changes or if some filtering occurs. The consequences will be less extreme, but still significant over time. Small spectral shifts can change photochemistry and biological tuning. Now consider the possibility of an engineered spectral filter in orbit shaping sunlight. This is the most flexible way to get any color sun without changing the star. In such a scenario, humanity could choose a spectral distribution to manage climate. For example, filtering out near-infrared could reduce heating because near-infrared is absorbed strongly by water vapor and surfaces. Filtering out UV could protect against skin cancer, but filtering also reduces energy available for photosynthesis. The design would involve trade-offs. But again, stay with the sun as other colors, not with engineering narratives. Mention only insofar as it defines a physically coherent spectral shift. Now return to the green filter. If one filters to green, the total photosynthetic productivity might decline initially because many plants are optimized for red and blue, but plants could adapt. Over centuries, agricultural species could be bred for green absorption. Over geological time, evolution could produce pigments optimized for green. The world could become dark-leaved to absorb green. Under green-only illumination, red fruits would appear dark. Pollination signals would change. Now, consider the effect on human psychology of monochromatic light. Monochromatic environments can be disorienting, reducing depth cues that rely on chromatic aberration and color contrast. But humans could adapt. More importantly, it would change the information content of scenes. But again, that is downstream. Now consider the appearance of the moon under different sunlight. The moon reflects sunlight. Under a red sun, moonlight would be redder, affecting night illumination. Under a blue sun, moonlight would be bluer. Nocturnal animals rely on moonlight spectrum. Predation patterns could change. Under a red sun, nocturnal illumination might be dimmer to human eyes if shifted to wavelengths rods are less sensitive to. Nights might feel darker even with a bright moon. Under a blue sun, moonlit nights might be brighter. Now consider the sky at night. Air glow and aurora depend on atmospheric composition and solar UV. Under a UV-rich sun, air glow could be stronger. Under a UV-poor sun, weaker. This affects the darkness of night skies, which affects navigation and ecology. Now deepen into the sun's emission lines. The Fraunhofer lines in sunlight are signatures of absorption. They also slightly change the spectrum's perceived color by removing certain bands. The strongest line invisible is the sodium D lines around 589 nanometers. These lines are narrow, but their presence contributes to spectral structure. Under different solar composition, line strengths change. Under higher metallicity, line blanketing in UV and blue increases. This can make the star appear redder. That can reduce UV reaching Earth even if temperature is the same. This could reduce ozone formation and vitamin D synthesis. Thus, a redder sun could occur without huge temperature change. Now consider the significance of the sun's color for agriculture in terms of plant action spectra and photomorphogenesis. Plants respond to red and far red ratio, which indicates shading. The ratio changes under canopies because chlorophyll absorbs red and transmits far red. Under a redder sun, the baseline red/far red ratio could change. Plants might interpret full sun as shade, causing elongation and reduced leaf thickness. This could reduce yield. Under a bluer sun, the ratio might shift differently. Now, consider the significance for animals. Many animals have color vision tuned to their ecological needs. Birds often have 4 cone types, including UV. Under a red sun, UV is lower, perhaps reducing UV-based signaling. Feathers might evolve different reflective properties. Under a blue sun, UV could be abundant, and UV signals could become more important. This could reshape mating systems. Now consider the significance for human-made color reproduction, like printing and digital displays. Displays emit light in narrow bands, red, green, blue. Under different ambient illumination, perception changes. Under a red sun, displays might appear different in daylight, requiring different calibration. Photography would require different color correction. But again, downstream. Now return to the climate again, but deeper into radiative forcing. Climate forcing depends on changes in net radiation at the top of the atmosphere. If the sun's spectrum shifts, the planetary albedo changes because albedo depends on wavelength. Even if total solar constant is unchanged, the absorbed solar radiation could change. For example, if the spectrum shifts to near-infrared, where ice is less reflective, the absorbed fraction increases, warming. If it shifts to blue, where ice is more reflective, absorbed fraction decreases, cooling. Thus, spectral shift is a forcing. Additionally, the distribution of absorption between atmosphere and surface changes, affecting lapse rate and cloud feedback. This is more complex than a simple forcing. Now consider the greenhouse effect in more detail. Greenhouse gases absorb in infrared, not invisible. But incoming near-infrared can be absorbed too. Water vapor has near-infrared bands. CO2 has bands around 2.7 and 4.3 micrometers, but those are longer than near-infrared. Still, some overlap exists. Under a red sun with more energy in near-infrared, more absorption occurs, heating the atmosphere. This could reduce the temperature gradient, potentially reducing convection. Reduced convection could reduce cloud formation, reducing albedo warming, or it could increase humidity, increasing clouds. The sign is uncertain. Now consider the effect on ice. Under a red sun, ice absorbs more energy and melts more. This reduces ice cover, reducing albedo, warming. A red sun could thus push Earth toward a warmer state, even if total energy is unchanged. Under a blue sun, ice reflects more, potentially cooling, but UV could be absorbed and cause photochemical changes on snow surfaces, affecting albedo. But overall, a blue sun might make ice more stable. Now, consider deserts. Deserts reflect visible and near-infrared differently. Under a red sun, deserts might absorb more, heating and intensifying convection, perhaps altering monsoon patterns. Under a blue sun, deserts might reflect more, perhaps cooling. Now consider clouds. Cloud droplets scatter visible light efficiently. In near-infrared, absorption by liquid water increases and scattering properties change. Under a red sun with more near-infrared, clouds might absorb more and reflect less, reducing their cooling effect. Under a blue sun, clouds reflect more, increasing cooling. This suggests that a red sun could warm Earth. A blue sun could cool Earth for the same total solar constant. This is a key insight and returns a theme. Spectrum matters, not just total power. Now return to Earth's biosphere. The distribution of available wavelengths affects not only photosynthesis, but also thermal regulation. Plants transpire to cool leaves. Transpiration depends on stomatal opening, influenced by blue light. Under a red sun with less blue, stomata might open less, reducing transpiration, increasing leaf temperature, potentially stressing plants. Under a blue sun, stomata open more, increasing transpiration, cooling leaves, but also increasing water demand. This could reshape ecosystems, favoring drought-tolerant species under red sun and water-rich ecosystems under blue sun. Now consider that many photoreceptors in plants and animals are tuned to blue because blue photons carry more energy and are more informative about daylight. Under a red sun, these systems might shift. The biological world could become more reliant on temperature cues and less on spectral cues. Now consider the possibility of life using infrared vision. On Earth, some snakes have infrared pit organs sensing thermal radiation, not reflected sunlight. Under a red sun, if visible is dimmer, perhaps infrared sensing becomes more useful. But thermal radiation from warm objects is in mid-infrared, far longer wavelengths than near-infrared sunlight. Still, the general environment could favor other senses. Now consider human health beyond vitamin D. UV influences immune function and skin. Under UV-poor sun, skin diseases could differ. Under UV-rich, melanoma risk increases. But again, downstream, Now, consider technology in terms of agriculture lighting. Under different sunlight, indoor farming might use supplemental wavelengths. Under a red sun, blue supplementation might be needed for plant development. Under a blue sun, red supplementation might be needed for flowering. This is known in horticulture. Red and blue LEDs are used to optimize plant growth. This provides a real-world analog of spectral tuning. Now consider the concept of other colors, not just as single colors, but as time-varying spectra. But the user asked for longest possible. Keep continuous. Now revisit the central concept. The sun is all colors combined. This phrase is true in a limited sense. The sun emits across visible wavelengths. But the physical reality is a continuous spectrum shaped by thermal emission and absorption lines. Human vision reduces this continuum to 3 signals. Thus, many different spectra can produce the same perceived color. The sun's color is thus a mapping, not a fundamental property. This leads to a slow revelation. Changing the sun's color in a way humans notice is not necessarily the most important change. Changing the UV fraction could be far more consequential even if the sun still looks white. Changing near-infrared fraction could alter climate and photosynthesis even if the sun still looks yellow. The world could be physically transformed while the sun's disk still looks familiar. Now consider that the sun's color seen from Earth is also affected by atmospheric water vapor, which absorbs near-infrared. But water vapor also has weak absorption in visible. Aerosol absorption can also change color. On humid days, sunlight can be slightly reddened. On clear, dry days, bluer. Under a different sun, humidity patterns could change, altering perception. Now consider the effect on sunrise and sunset in detail. At sunset, sunlight passes through more atmosphere. Blue light is scattered away, leaving red. Under a blue sun, there is more blue to scatter, so the reddening is stronger, potentially making sunsets more red. Under a red sun, there is less blue to scatter, so sunsets might be less dramatic, but aerosols can add red. Under a UV-poor sun, ozone might be lower, reducing certain absorption that contributes to red sunsets. Under a UV-rich sun, ozone might be higher, enhancing certain reds. Now consider the effect on the sky's polarization. Polarization patterns are produced by scattering, strongest at 90 degrees from the sun. Under a blue sun, scattering is stronger. Polarization could be stronger, aiding navigation for animals that use it. Under a red sun, polarization might be weaker. This could influence insect navigation, and thus pollination and ecology. Now consider the effect on human-made navigation. Polarization sensors could be used, but again downstream. Now consider a deeper astrophysical constraint. If the sun were hotter and bluer, it likely would be more massive and have a shorter lifetime. If cooler and redder, less massive and longer lived. But since we are changing the sun, Earth's orbit might change if mass changes. But gravitational mass is separate from spectral distribution. Still, in real stars, mass ties the temperature. To keep Earth's orbit stable, one might assume mass remains the same. But a star of the same mass cannot have a very different effective temperature without being at a different evolutionary stage. A cooler star of same mass could be in a later stage, expanding. A hotter star could be earlier or different composition. These complexities show that sun color implies stellar evolution, but keep anchored consequences for Earth under different spectra. Now consider a later stage sun that is cooler but larger, such that luminosity could remain similar. That resembles a subgiant. Such a star might have different variability, but avoid general stellar evolution. Now consider the effect on the spectral distribution of UV and X-rays from the corona. If the photosphere is cooler, the corona might still be hot, but activity could change. But we can treat high-energy output separately. But the user wants only consequences related to spectrum and activity. So mention that UV and X-rays are tied to activity and could change, affecting the ionosphere and material degradation. Now consider auroras and power grids again. Power grid vulnerability is tied to geomagnetically induced currents, which depend on solar storms, not spectrum. But UV influences ionospheric conductivity, which affects current systems. A UV-rich sun could increase conductivity, potentially influencing how currents close. This could change storm impacts. But this is secondary. Now consider that a bluer sun might also emit more in the shorter wavelengths that heat the upper atmosphere, expanding it, increasing drag. This affects satellite orbits and space debris decay rates. Under a bluer sun, debris would decay faster, cleaning low Earth orbit. Under a redder sun, debris would persist longer, increasing collision risk, unless activity differs. Now, consider the effect on radio communications. The ionosphere's critical frequency depends on electron density. Under a UV-poor sun, HF radio might be less reliable for long-distance reflection. Under a UV-rich sun, it might be more reliable but also more variable due to increased activity. But again, anchored. Now consider the Earth's biosignature detection. Under different sun, the reflectance of vegetation might shift. The red edge is tied to chlorophyll and near-infrared reflection. Under a red sun, the edge might shift to longer wavelengths if pigments adapt. Astronomers could detect a different edge. This is important for interpreting exoplanets. It also shows that life adapts to the star spectrum. Now consider the human sense of color names. Under a red sun, the concept of blue might be rare in nature and the language might have fewer terms. On Earth, some languages have fewer color terms and acquire them in a predictable order, often with dark/light first, then red, then green/yellow, then blue. This is related to salience in environment. Under a red sun, blue salience might be reduced, perhaps delaying the emergence of a word for blue. Under a blue sun, perhaps blue is prominent and early, but this is cultural and less central, mentioned only lightly. Now return to the question of green sun again, but deeper into physics. Could a star emit green-dominated light naturally? Certain nebulae emit strong green lines, such as oxygen emission at 500.7 nanometers in planetary nebulae, giving a greenish hue in telescopic images. But stars are dense, thermal sources. Line emission is not dominant. Therefore, a green sun would not be a normal star. It would require a filter or a non-thermal emission process. Thus, the coherent scenario is filtering. Filtering could also create a purple sun by allowing red and blue but blocking green, producing magenta light, which is not a spectral color, but perceptual combination of red and blue. Under magenta illumination, the world would look strange. Many green objects would appear dark. The sky could be purplish. This again shows that perceived color can arise from missing bands. A cyan sun could be created by transmitting blue and green, blocking red. This would make daylight cold and aquatic. Under cyan light, red objects would appear dark. Blood and skin could look different. Photosynthesis might adapt. Under cyan, the photon energy is higher than red, which would be beneficial for certain reactions but also damaging. Now consider the appearance of fire under different illumination. Fire emits its own light, a spectrum based on temperature and emission lines. Under a red sun, fire might stand out less in red bands but more in blue. Under a blue sun, fire's warm emission might look more orange by contrast. But this is a minor detail. Now consider the effect on human-made lighting at night. Under a red sun, the baseline adaptation of the visual system might shift, affecting how artificial lighting is perceived. But again, minor. Now consider the effect on plant seasonal cues. Many plants use photoperiod to time flowering. Photoperiod measurement relies on light intensity and spectrum. Under a different spectrum, the thresholds might change. This could change the timing of seasons in ecosystems. Now, consider the effect on animal migration. Many animals use polarized skylight and spectral cues at twilight. Under a different sun, twilight spectrum changes, possibly disrupting migration cues. Over time, adaptation occurs. But again, anchored. Now consider the effect on human circadian disorders. Under a red sun, less blue light might reduce seasonal affective disorder. Actually, SAD is associated with low light in winter. Blue light is effective for therapy. Under red sun, winter light might be less effective, increasing SAD. Under blue sun, perhaps less, but speculative. Now, consider the effect on the greenhouse effect in terms of outgoing radiation. Outgoing radiation depends on surface temperature, not on incoming spectrum. But incoming spectrum influences temperature. However, spectral shifts can change the vertical heating profile, which changes lapse rate, and thus outgoing radiation. The interplay is complex. Now consider the effect on clouds in more detail. Cloud droplet size distribution affects scattering. Under different UV, aerosol formation changes, affecting droplet size. Smaller droplets reflect more sunlight. UV-rich sun could produce more oxidants, producing more sulfate aerosols, increasing cloud condensation nuclei, producing smaller droplets, increasing cloud albedo, cooling. This could counteract warming. Under UV-poor sun, fewer aerosols, larger droplets, less reflective clouds, warming. This is a plausible pathway for spectral influence on climate. Now consider the effect on photochemical smog. Under UV-rich sun, smog formation is faster. Under UV-poor, slower. Urban air quality would differ. Now consider the effect on plant secondary metabolites. UV stimulates production of protective compounds, which can affect taste and nutrition. Under UV-rich sun, plants might be more bitter and antioxidant-rich. Under UV-poor, perhaps less. Now consider the effect on ocean color. Ocean color is used to infer chlorophyll concentration from satellites. Under different sunlight, ocean color signatures would change. But also, phytoplankton pigments could change. Under red sun, pigments might shift. Ocean color could be different. This could affect heat absorption because pigment concentration affects albedo. Now consider the effect on snow algae. On Earth, snow algae can darken snow, reducing albedo, enhancing melt. Under red sun, snow melt is already easier due to infrared absorption, and snow algae could further accelerate melt. Under blue sun, snow might be more stable, but UV could inhibit algae. This could change cryosphere dynamics. Now consider the effect on human eyesight in terms of cataracts. UV contributes to cataracts. Under UV-rich sun, cataracts might be common, leading to evolutionary pressure for protective eyelids, melanin in eyes, or behavior. Under UV-poor sun, less. Now consider the effect on animals with UV vision. Under UV-poor sun, their UV vision is less useful, might shift. Under UV-rich, more. Now consider the effect on insects. Insects are often attracted to UV. Under UV-rich sun, insect behavior changes. Under UV-poor, less. Pollination networks change. Now consider the effect on the ozone hole. Under different UV, ozone dynamics differ, but too detailed. Now consider the effect on the color of the sun itself when viewed through clouds. Clouds scatter light and can make the sun appear whiter. Under a red sun, clouds might scatter and whiten, making the sun appear less red. Under a blue sun, clouds might whiten too. This affects perception. Now, consider the effect on human art and photography again. Under a red sun, the dynamic range in blue is reduced. Under a blue sun, dynamic range in red is reduced. But again, downstream. Now consider the effect on thermal comfort of buildings. Under red sun with more near-infrared, windows would transmit and absorb differently. Glass transmits visible but blocks some infrared depending on coatings. Modern low-E coatings reflect infrared. Under red sun, such coatings would be more important. Under blue sun, less. Now consider the effect on agriculture in greenhouses. Greenhouse glass transmits visible but blocks UV. Under a UV-rich sun, greenhouses would protect. Under UV-poor sun, less difference. Now consider the effect on the color of plants in space. In space, plants under artificial lighting can be different colors depending on spectrum. Under red and blue LED, plants look purple. This shows how illumination changes appearance. Now consider the effect on animal camouflage. Under red sun, backgrounds are warmer. Animals might evolve different pigments. Under blue sun, different. Now consider the effect on human skin phototype distribution. Under blue sun, more melanin. Under red sun, less. This affects vitamin D. Now, consider the effect on microbial mats and early life. Early life evolved under a sun with different UV because the atmosphere lacked ozone. UV was strong. Life evolved UV protection. Under a blue sun, perhaps similar. Under a red sun, perhaps less. This could change early evolution. Now, consider the effect on the origin of life. UV can drive prebiotic chemistry. Some hypotheses suggest UV helps synthesize RNA building blocks. Under a red sun with low UV, origin of life pathways might differ. Under a blue sun, UV-rich could promote, but this is a different topic. It still relates to sun spectrum and life. Keep brief. Now consider the effect on human color vision evolution. On Earth, trichromacy in primates evolved partly for fruit detection. Under different illumination, fruit colors might differ, affecting selection. Under red sun, red fruits might be more salient. Under blue sun, perhaps different. Now, consider the effect on marine animals. Many marine animals are blue because blue light penetrates. Under red sun, deeper penetration is reduced, perhaps favoring different colors and behaviors. Now, consider the effect on coral reefs. Corals depend on symbiotic algae. Light spectrum affects algae under red sun. Shallow waters might heat more due to infrared absorption, stressing corals. Under blue sun, deeper penetration might help, but UV could damage. Now consider the effect on clouds again, but in terms of cloud absorption. Cloud water absorbs in near infrared. Under red sun, clouds absorb more, heating clouds, perhaps affecting stability and precipitation. Under blue sun, clouds reflect more and absorb less, cooling. Now consider the effect on stratospheric water vapor. Under UV-rich sun, more photolysis. Under UV poor, less. Now consider the effect on the Earth's energy budget in terms of spectral weighting. The solar constant is about 1361 W/m²2 at top of atmosphere, but only about 43% is visible, about 52% infrared, and about 5% UV. Under a red sun, the UV fraction could be lower, infrared higher. Under a blue sun, UV higher, infrared lower. This changes how energy is partitioned. Now consider how humans measure the sun spectrum. Instruments like spectrometers disperse light via prisms or diffraction gratings, measuring intensity as a function of wavelength. In space, solar observatories measure across UV to IR. On Earth, spectral radiometers measure surface spectrum. Color is quantified using tristimulus values. Astronomers use photometric filters, but no need to reference external tools. Now consider that human perception of the sun's color is influenced by adaptation and by glare. The sun is too bright to see color directly. One sees it through scattering or filters. Thus, the color of the sun is often inferred from sunlight on white objects. Under a different sun, white objects would appear tinted, but color constancy might adapt. Now consider the difference between daylight and sunlight. Daylight includes direct sunlight and scattered skylight. The spectrum of skylight differs from direct sunlight, being richer in blue due to scattering. Under a red sun, skylight would be less blue. Under a blue sun, skylight would be very blue. Daylight and shade is thus sensitive to spectrum. This influences photography and perception. Now consider the effect on snow and ice again in terms of absorption. Under red sun, snow absorbs more near infrared. This warms it, melts it. This reduces polar ice, raising sea level, changing climate. Under blue sun, snow reflects more, stabilizing ice, potentially lowering sea level. Now, consider the effect on plants in polar regions. Polar regions have low sun angle. Under blue sun, scattering is stronger, perhaps providing more diffuse light. Under red sun, less. This affects polar ecosystems. Now consider the effect on atmospheric circulation. The distribution of heating between equator and poles drives circulation. If spectral changes alter albedo in cloud cover differently at different latitudes, circulation changes. Under red sun, polar ice less reflective, poles warm, reducing equator to pole gradient, weakening jets, perhaps making weather patterns more stagnant. Under blue sun, poles colder, stronger gradient, stronger jets, more storms. This is plausible. It connects spectrum to weather. Now, consider the effect on extreme weather. Under stronger gradients, more storms. Under weaker, fewer. But also humidity matters. Under red sun, more near-infrared could increase atmospheric heating and humidity, potentially increasing rainfall. Under blue sun, perhaps less humidity if greenhouse changes, but uncertain. Now consider the effect on evaporation and precipitation patterns. Under red sun, if surface heating is reduced due to atmospheric absorption, evaporation could decrease. But if surface warms due to reduced ice albedo, evaporation increases. Complex. Now consider the effect on deserts' expansion. Under different climate, deserts expand or contract. Now consider the effect on human technology in terms of agriculture. But again, now consider the effect on the color of the sky itself. Under red sun, the sky might appear less blue and more pale, perhaps yellowish because scattering of shorter wavelengths is reduced. Under blue sun, the sky could be deeper blue, perhaps even purplish near the zenith if violet is abundant. But human eyes are less sensitive to violet, and atmospheric ozone absorbs some, so perhaps deep blue. Now consider the effect on the color of clouds. Clouds are white because they scatter all visible wavelengths similarly. Under red sun, clouds would still appear white, but illuminated with warmer light, appearing peach at sunrise. Under blue sun, clouds might appear cooler. Now consider the effect on the appearance of shadows under clouds. Under overcast, light is diffuse and spectrum is modified. Under different sun, the overcast spectrum differs. This affects mood. Now consider the effect on human sleep. Under red sun, less blue, melatonin suppression less, perhaps easier sleep. Under blue sun, harder sleep, requiring behavior changes. But again, now consider the effect on plants in terms of photoinhibition. Under blue sun, more high-energy photons, photoinhibition risk. Plants might have lower maximum photosynthetic rates to avoid damage. This could reduce productivity. Under red sun, lower photoinhibition, perhaps higher rates, but lower photon energy might limit. The optimum is complex. Now consider the effect on animal vision underwater. Under red sun, less blue to penetrate. Underwater scenes darker. Under blue sun brighter. Fish might evolve different pigments. Now consider the effect on algae. Many algae use different pigments. Under red sun, red algae might dominate. Actually, red algae absorb blue-green and reflect red, suited to deeper water where blue penetrates. Under red sun, blue is less, so perhaps different. Now, consider the effect on human agriculture of algae. But no, now consider the effect on atmospheric CO2 absorption. CO2 absorbs in near-infrared around 2 micrometers. There are bands. Under red sun, more energy in those bands could be absorbed, heating atmosphere. Under blue sun, less. This influences greenhouse. Now consider the effect on water vapor absorption. Under red sun, water vapor absorbs more incoming, warming air, increasing humidity. Under blue sun, less. Now consider the effect on relative humidity. But now consider the effect on lightning. Lightning depends on convection. Spectrum influences convection via heating. Now consider the effect on vegetation distribution. Under red sun, maybe more drought stress. Under blue sun, maybe more transpiration. Now consider the effect on carbon cycle. Under red sun, lower productivity might reduce carbon drawdown, increasing CO2, warming. Under blue sun, higher productivity might draw down CO2, cooling, unless UV damage reduces productivity. Now consider the effect on nitrogen cycle. UV influences nitrate formation in atmosphere. Now consider the effect on photolysis of nitrate. But too much. Now consider the effect on air glow again. The thread continues.